So other very interesting distribution is exponential distribution. Okay, so let's talk about that. So okay, so again let's plot the PDF of exponential distribution. Okay, so plot PDF of exponential one. Okay, okay. So we can use dexp. Okay. So exactly, for PDF, put D in front and exp. Okay, so if you want to take help, you can check that out. Okay, dexp. Let's run this. Okay, this is exponential distribution. Okay, okay, so you have to specify the rate. Okay, mean is 1 by rate. Okay, in exponential distribution. So exponential distribution is actually, you can think of it as a continuous time analog of geometric distribution. Okay, so it's like you want to model situations like waiting time. Suppose you are waiting for a bus to arrive at the bus stop, or you're waiting for a customer to arrive at your store. Okay, so the amount of time that you'll have to wait, can be modeled using exponential distribution. Of course, there are certain limitations. Of course, there is something called memoryless property, which is a unique feature of exponential distribution. Okay, so we'll talk about that as well. But the idea here is just that if you want to model a situation where you're trying to wait, where you're waiting and you're interested in the amount of time you have to wait for an event to occur, then this is a commonly used distribution. There are other distributions also that you can use, let's say gamma or something like that, but this is something which is most commonly used. Okay, exponential. Is that okay? So this has something called memoryless property. Now, what is memoryless property? Let me just explain quickly in terms of, so geometric, right? Geometric is number of tosses, number of failures until first success in successive Bernoulli P trials. So that's the interpretation of geometric, right? So yes, okay. So like for example, if I toss a fair coin, okay, how many times I have to observe a tails till I get the first heads? That's a random variable, right? So if I keep tossing a fair coin successively, the number of tails that I observe before observing my first heads, that's a random variable. It's possible that I might observe just zero number of tails. I just get heads in the first go. Okay, it's also possible that I might have to wait for 10 tails before observing my first heads. So it's a random variable. Okay, now suppose I ask you, in case of geometric, suppose I ask you this, that what is the probability that you will observe heads, what is the probability that you'll have to wait, or basically you will at least 3 times before observing the first heads? You'll give me some answer. Let's not find out that answer. Let's just say there is some answer to that question. Suppose you toss the coin 5 times and you observe just tails. Suppose now I came back and asked you this particular question again, that okay, what are the chances that you'll observe at least 3 more tails before observing the first heads? Will your answer change? No. That is memoryless property. So the thing is that if you have already failed few times, okay, then the chances of observing some an additional number of failures, that will not change. That's memoryless, because whatever is gone. Now it's just like starting afresh all the time. Exponential distribution also has that property, and in fact it is the only positive random variable, continuous random variable, that has that property. Geometric random variable is a discrete random variable. It also has the property, but this is among the continuous ones. Okay, so if you are interested in the proof, you can actually watch lectures on by Blitzstein. Blitzstein lecture also has a proof. This uniquely characterizes the exponential distribution. Okay, this memoryless property. Okay, but what we are going to do here is this. we'll just see its, the shape, and we'll just basically figure out what happens if the rate goes up, what happens to the PDF if the rate goes down. We'll figure out the other things, we'll figure out the probabilities associated with it. So of course, but in applications, the use of it is that you actually use it for waiting, modeling the waiting time. Is that okay? So you can think of, in economics, you can actually think of, maybe you are trying to innovate something, okay, and you are doing this experiment, and how much time you'll have to wait for the invention to occur. It's like, this is, I'm sure that this is, and this is something that you'll also find in patent race models, I mean R&D models, where you're just trying to, you're just waiting for, some invention to occur or something like that. Okay, so all this is waiting time. Of course, patent race is basically among players. Okay, so the thing is that then players will be actually competing for each other, and whoever is going to invent first is going to get the patent, something like that. So that's actually kind of another very interesting application of this in economics that you can actually think of. Okay, you can use it in patent race models. Is that fine? Okay, so this is actually, for modeling waiting time. Is that clear? Okay, and the parameter associated with it is the rate parameter. Okay, lambda is the rate parameter. So the rate of success. So if the rate at which you succeed is, let's say, you make 10 inventions per year. Okay, suppose that's the rate of success, 10 inventions per year, or 10 research papers per year, or whatever. Okay, so then how much time will you'll have to wait to see your first paper or first invention? I mean, how much time will you have to wait in, like, I mean, 1 month, 2 months? That's a random variable, right? Okay, so of course, if the rate of success goes up, then the amount of waiting time goes down. Is that okay? So you keep these things in mind, and then we'll just do the plotting. Okay, is this fine? Have you understood this? Okay, great. Okay, so let's plot exponential 1. So the rate is 1. Okay, let's just plot that. Okay, so note that it is a positive random variable. Okay, so it only takes positive values. Okay, so exponential 1, we can just keep the size of the domain. So basically it can take any value from 0 to infinity, but we don't want to plot it from 0 to infinity. We'll just keep some range. We'll just plot it from 0 to 5 or something like that. Okay, that should work. Okay, so x is seq 0 to 5. Okay, 0.01. Okay, so the increment is by 0.01. Okay, and then we want to plot the PDF. So dx is, what is this? Okay. Dx is dx is dexp, right? Okay, dexp. Okay, and rate is 1, so we don't have to specify that actually. And the next thing that we want to do is just plot the density function. So we'll create the data frame. Okay, let me just use the same code because it's the same code. Okay, so I think this is it, right? Okay, let's run this. Okay, so this is how the density function looks. So if you remember, the density function of exponential 1 is e to the power minus x, and e to the power minus x is a decreasing function. This is exactly the plot of e to the power minus x. Is that okay? Fine. Now let me ask you this. Suppose I superimpose on this another plot. Okay, I superimpose on this another plot, another line plot. And what I'll do is this time I'll plot a density function of a random variable where the parameter is 2. Instead of 1, the parameter is 2. So what do you expect? What do you think will happen to the density function? Will it become more steeper than this, or will it become flatter than this? So the rate parameter has gone up. Rate is now 2. So it will be steeper, right? So basically more successes, the chances of success is basically occurring in the next 1 minute is going to be higher. Is that okay? Fine. So basically there'll be a higher density close to 0 and lower density away from 0. Is that okay? Clear to everyone? Close to 0, there'll be high density. Yes or no? So I'll superimpose on this another plot, geom underscore line. Okay. So what I can do is, let me try this. Aesthetics x equals x. Okay, and y equals dexp, and the rate this time is 2. Okay, x2. And let me change the color. Let me put the color attribute, color equal to red. Okay, so this one, let me just have a red color on it, and this will give me, I think this should, but let's just run this. This should give me two density plots in the same graph. Okay, so let's just run this. Okay, you can see this. Okay, so the red one has a higher success rate, okay, compared to the black one. Is this clear? Okay, that's why it's more steeper, right? Because you are more likely to observe success quickly. Okay? I mean, when the rate is high. You know, is this fine? Okay.